Hello and welcome to my talk about ALEA, the agnostic domain-specific language for implementing attacks in an automotive use case. My name is Wolschke, and this work has been conducted together with AWSMA and Fraunhofer IESE as part of the EU project SecRadars. As the agenda, I would like to give you the motivation why we created the attack language, which concepts we have, how the design and compilation process looks like, and how we applied the language to one use case. The idea of ALEA is to be agnostic to SUTs. Within our problem setting, we have multiple vehicles which are our SUT and which should be tested with the same attack scenario. As we don't want to write one test script per SUT with the same test scenario, we write the test scenario in the DSL and translate it automatically to the test scripts that we want to have. Within the translation process, we add specific information about the test environment and specific information about the SUT. When we set up such a language, it is important that we have a flexible execution. So we need to react dynamically to SUT responses, and we need to foresee different architectures of the SUT. The test scripts need to be adapted by the DSL translation so that the right tools are selected, as well as configurations and parameters. We want to apply this language to the automotive sector, and we assume that an SUT consists of several buses, such as CAN, MOST, and FlexRay, as well as gateways and ECUs. The concepts of the DSL are to have multiple attack steps which are executed in a sequence. Each attack step is defined by a precondition, which then may trigger an action, and afterwards a postcondition can be called. With the pre and post conditions, we want to be flexible and to react to different SUT settings. The action may call a specific tool which is defined within the DSL translation process. We also introduced a special failure semantics. So if an attack step is not executable, as the precondition is not fulfilled, or as the post condition fails, then the next step is executed anyhow. We want to have predefined support for automotive bus systems, which especially considers that we may have predefined pre and post conditions and predefined actions, such as the cyclic sending of bus messages. ALEA has been implemented with the Xtext framework. It is an Eclipse-based framework for defining DSLs. Within the framework, we define commands explicitly, and we link pre- and post-conditions via labels to actions. We also define that we have variables which are defined implicitly. A variable may be an auxiliary variable or system variable. The definition of variables helps us to detect conflicts automatically and to translate variables to executables. What you see here is an example of ALEA. Within the actions list, we have 4 actions which are executed in a sequence. At first, we open the Android debug bridge with a specific IP address, and we exploit a vulnerability vulnerability to get a connection. If the connection is present, so if the precondition is fulfilled in here, then we exploit that we could execute a script and execute also the command of superuser. In the next step, we ask which user we are. So we execute who am I on the target system. And if the user is root, then we know that we had success with this kind of command. Finally, we may call a list command so that we exploit that we can execute a further command. Such an ALIA script is translated automatically to a JSON representation, which you see here below. And within the translation, you see that the number of, or the list of tools is filled out, and also that the necessary parameters are set. This JSON file is taken by an attack execution engine to be executed within the test. We applied the ALIA language to one use case in which we want to change the vehicle speed via the infotainment head unit. Therefore, at first, the attacker used the mobile phone to get an access to the infotainment head unit. Within the script of ALIA, you see that at first, a scan of the Bluetooth interface takes place. Afterwards, a vulnerability should get exploited such that the shell is accessed via the attacker. The attacker would then use the shell to open an Android hotspot and to establish a Wi-Fi connection. This Wi-Fi connection is then used to install attack scripts on the target. After the attack scripts are installed, the CAN bus can get attacked, as you can see here with the command exploit, which gives a certain car CAN attack script. Within the example, it has been shown that ALIA can be used agnostic to the SUT, and also that we can use the pre and post conditions to react dynamically to different execution parts. In example, even if you cannot access the car via the Bluetooth connection, you could show that the rest of the commands is executable and that there's no security measure in place to avoid such an attack. Further, the attack hides the details of the Bluetooth and the CAN interface. An example, the message ID of the CAN messages. And so the ALIA DSL script is agnostic to the implementation. What we have achieved so far is that we have an SUT agnostic attack language, which has flexible design elements to address the topic that specific and test environmental data are specific to the SUT. Via pre and post conditions and the execution semantics, we react flexible on possible changes and deviations of the SUTs. With the use of Xtext and the Eclipse-based support, we can have scripts with attack scripts with nice usability features, such as the automatic detection of variables that have been defined. As a future work, we want to roll out the ALIA language to the systems that we have. That means we apply it to multiple SUTs And therefore, we also expect that we will have more features as more tools for commands. If while statements, we also want to integrate versioning support and many other features. If you are interested in the work of SUT agnostic attacks, we welcome you to discuss the issue with us. Thank you for your attention.